get state-of-the-art AI coding velocity in 2026, the marketing pages tell you it costs a flat $20 a month. But if you look at the billing dashboards of engineering teams running true agentic workflows, the reality is entirely different. Power users are routinely getting hit with $300 to $2,000 monthly API bills just to keep their AI environments running. This waterfall chart breaks down where that money actually goes. You typically start with the standard subscription stack, a $20 Cursor plan, $20 for Claude Pro, and $10 for Copilot. Then the real driver hits, a massive $300 to $2,000 in API overages. Those individual subscriptions only grant you base access with heavy rate limits. The moment you need an agent to operate autonomously without pausing, you have to switch to API billing. You are now paying for every single piece of data the model processes. That $20 tier covers the basic entry point. If you need a coding agent to work autonomously without hitting a hard ceiling, your monthly costs shift from a fixed subscription to a direct variable of your usage. A coding agent generates code, but that is the smallest part of its job. It spends the vast majority of its tokens reading files, searching your codebase, executing commands, and planning its next move. Writing the code is cheap. Processing the massive volume of context required to understand where that code goes is where the money is drained. Studies show up to 70%. A session that starts at 5,000 tokens per call curves exponentially upward, heading 200,000 tokens per call by turn 50. Now factor in what happens when the agent gets stuck. It tries an approach, fails, and tries again. Every failed attempt is added to the context history. The context grows, the reasoning degrades, and each subsequent iteration costs more than the last. You are paying for the exact same history over and over again. Unchecked context size turns micro-wastes on every turn into hundreds of dollars of unnecessary overhead. We can evaluate the technical levers available to cut these API costs using this quadrant chart. We are mapping implementation friction on the x-axis against potential cost savings on the y-axis. The first high-return strategy drops into the top left corner. Model routing. There is up to a 50 times price difference between models. OpenAI's GPT-4 Plate 1 Nano costs just 10 cents per million input tokens, while flagship models like Claude Opus 4.6 cost $5. To capture these savings, you implement middleware or hard-coded rules that actively classify requests. You send simple edits, documentation, and test runs to the budget models, and reserve the flagship models strictly for complex, multi-file reasoning. The trade-off is manual oversight. You abandon the convenience of auto settings and accept the risk that a complex architectural task might accidentally get routed to a lightweight model, degrading your output. But getting this right yields an immediate 50 to 70% cost reduction. Paying flagship prices to fix a one-line typo is the largest avoidable waste in your toolchain. Returning to our quadrant chart, our second strategy drops into the high-effort, high-impact zone, context compaction. This requires setting up specialized middleware that systematically reviews your conversation history. It verbatim deletes irrelevant CLI noise, failed attempts, and outdated planning before it sends the next API call. This intervention physically breaks the exponential cost curve we saw earlier. By shrinking the payload on every turn, you can save up to $60 on a single long development session. The catch is the setup friction of integrating third-party SDKs, along with the risk that your compaction tool might delete a crucial constraint you established early in the prompt. You are shifting the burden of memory management away from the API billing meter and onto your local architecture, trading initial setup friction for long-term session affordability. Back on our chart, a third node lands near the top left for low effort and high impact, prompt caching. This requires you to standardize your massive system documents and context instructions so they are sent exactly the same way on every single API call. When you do this, providers automatically recognize the repeated input and apply a massive 75 to 90% discount on those specific tokens as long as they stay in active memory. Warning tone. But this dictates your physical working pacing. If you step away for over an hour, the cache clears, and you pay a premium penalty to rewrite it on your next query. Prompt caching financially rewards highly structured, continuous development sprints and heavily penalizes sporadic, interrupted coding habits. The final node on our chart drops into the high-friction, high-impact zone, batch APIs. This involves taking massive, non-urgent workloads, like generating tests for an entire codebase or running a bulk refactor, and routing them through deferred provider queues. Pushing tasks through these queues guarantees a flat 50% discount on both your input and output tokens. The cost of that discount is latency. Results can take up to 24 hours to return. This makes batching completely incompatible with real-time editor autocomplete or flow state debugging. Batching requires you to stop treating AI as a real-time pair programmer and start managing it as a background worker. It strictly saves money on time-insensitive tasks. Implementing all 4 of these levers at once requires substantial engineering overhead. You need to choose a specific path based on your primary constraint. This decision tree flowchart maps out the 2 main paths. The top node asks, "What is your primary constraint?" and splits into 2 options: strict budget predictability on the left and max agentic ROI on the right. Let's look at the predictability seeker. This profile typically applies to independent developers or teams operating on strict budgets. To secure predictability, you opt out of raw pay-per-use APIs entirely. You commit your workflow to fixed ecosystem platforms, like the free Google Antigravity preview or a capped Claude Max plan. This guarantees your bill will never spike, but you are trading architectural control for opaque, vendor-enforced rate limits that will inevitably throttle your output during peak coding hours. On the other side is the systematic optimizer, a profile suited for team leads and agentic power users. This approach utilizes pay-per-use APIs, but surrounds them with strict guardrails, actively enforcing aggressive model routing and context compaction middleware across the team. This maintains a high coding velocity. You can run deep, multi-file agent loops without hitting rate limits, all at a fraction of the standard retail cost. To achieve this efficiency, you have to stop treating AI as a magical plug-and-play subscription. You must manage it as internal software infrastructure that requires constant auditing and tuning. Architecting your toolchain to eliminate context waste is the most direct way to scale. You stop paying for redundant subscriptions and start maximizing the value you get back from every single token.